we want to see then what the angle is between those two arrows. If they're right on top of each other, then the wave fronts would be right on top of each other too. But if those arrows are slightly out of step when it starts, there's an angle between them, then there'll be a colour. There'll be what's called an interference. So we're going to look at this film thickness D, and the first thing we do is we figure out what the difference the light had to travel between this one, and this guy had to come down and back up. So we start with the idea that the path difference between them was 2D. Went down, it came back up. Well, how many wavelengths could you fit in there? That's another interesting thing, because one wavelength represents the arrow going around the circle once. So how many wavelengths? Well, we divide by whatever the wavelength is in the oil. Like I said, it's smaller than it is in the air. Now, as there are 2 pi radians, because that's how we figure out angles in the whole circle, then if this is the fraction, the number of wavelengths that fit there, and we times it by 2 pi, we get what is called the phase difference. And that's the difference between the 2 arrows. Now, I've actually missed a few things here. I've just simplified that, 4 pi d over lambda oil. I've missed a few things here, which is that lambda oil is a bit tricky. What's the wavelength of red light in oil? Well, I don't know. I'd much prefer to figure it out for air. So I'm going to convert. I'm going to use year 10 GCSE, IGCSE refraction, which is the ratios between the refractive indices, is the reciprocal of the ratios between the speeds. And if I figure that out, the speed is the frequency times the wavelength. The colour certainly does not change when something refracts from your refraction experiments. You put green light in, you get green light out. So these don't change. I can not worry about those. And that then equals the ratio of the wavelength. So I then rewrite that down there and rearrange it down here. So I can replace my lambda oil on the bottom by timesing it by refractive index of oil over air, but that's 1, so we can forget that. And then the wavelength of the light in the air. Then I replace that with that, which although it looks a little bit more complicated, is easier to deal with intuitively because people have a better grasp of wavelengths in air and space than they do in oil. We're forgetting one last thing though, which is that, if you remember, the amplitude, the wave here flipped by pi. So it actually flipped everything that was up here, went to down here. If you imagine the wave going back and forth like this, but actually it's going up and down. 3D is hard to do on 2D. And we then need to add a further pi onto it because of that change in phase at the reflection. So now we get this big beast here, which is the phase difference between the 2 waves. The one that hit the top and then the one that went through the top. Hit the back one, came back up through. And that's what we're left with. Now, I said we're going to add some arrows together that represent the amplitudes. Here's amplitude 1 from, say, the surface A. Here's amplitude 2 from surface B. And I used this guy, which is the cosine rule. And this cosine would be this angle here. So here's my vector addition of those 2 amplitudes. And I would actually really need this angle here, but I've calculated this angle here. It's okay though, because actually that A2, we're going to say that that one was the one that flipped, and we're going to put that one over here. So then if we work it out, that is the right angle, and the whole thing then comes out as, let me go back one, that the intensity of the 2 combined is equal to the amplitude squared of the first one, the amplitude squared of the second one. Oh, sorry, so this intensity is the amplitude squared, the resultant amplitude squared, which I said was the intensity, right? Minus 2, the 2 amplitudes together, cosine the angle there. But I said that one of them flips, so this minus sign actually turns into a plus sign down here, and then I'm done. So you don't have to do this, it's okay, but I wanted to show you the derivation. The intensity of the light that comes back depends upon the thickness of the film, and it also depends upon the wavelength of the light. If you didn't get any of that, I do that because this is a science talk, but if you didn't get any of that, get what I just said. That the thickness of the film and the wavelength of the light, therefore the frequency, the colour, determines the intensity of the light that comes back. That's going to be vital for the last part of the talk. Now, what I've done is I've graphed that using Excel. I didn't want to do all the numbers myself. And I've done it here. I've taken all the frequencies of visible light, and even some that are a little bit on the fringe. And there's the big beast of the equation. The two intensities which we worked out before, which were 4% and 0.38% roundabout. And then I've done all of that cosine rule stuff. Be careful not to screw it up, so I click over there. I then tried to plot the intensity of the light that you can see against the various different colours. And I've used the picture in the background to tell you. So this stuff here, 420, 440, 460 is blue in nanometers for wavelengths. This is green, further over is red. And if I then try and change various parts of it, so if I go down here, thickness of film, I can change that parameter. Oh dear, it looks like I'm changing the equation. I can hit escape. Yeah, cool, right, down there. Thickness of film. Now I put 1,000 nanometers, micrometer. So you can already tell that I'm going to tell you that these are really thin films, really thin, micrometer in thickness. If I put any more in, if I got just 2 orders of magnitude, that's 100,000 nanometers, then I get a mess. And firstly I get a mess because I haven't used fine enough grains. I've used 1 nanometer steps in my calculation. When I get a mess, that means that if the thickness of the film is 100,000 nanometers, you get loads of different colours coming back. Loads and loads of different ones. And if I make the film thinner, those maxima that come back are less frequent. So there's more destructive interference for all the frequencies than there is constructive interference. Incidentally, if you're worried that it's 16% coming back, then don't, because we started with 4 and we started with 4, you might think that would add to a maximum of 8, but it's okay because we have to square the amplitudes and then you get the intensity, so it's kind of counterintuitive. But it's alright, and then the energy coming back the other way will be 100 minus 16% the intensity going back, so it's fine. Now I've animated it over here. Ooh, wow, crazy stuff. And I've taken screen captures, very laborious. I took screen captures, and you can see the film thinning. So now if you follow in the bottom bar and simultaneously look at the graph, it's now at 800 nanometers, and there are still some peaks. So there are still 3 peaks there. And you know that when you combine several different colours of light together, you see white. So this isn't really thin enough yet. We've got blue light, we've got kind of green light and red light there, and if you add those together, you pretty much see white light. So we need to go thinner. And as we get thinner, I want you to concentrate on this one. I'm going to show you this one in a minute. We've got blue, no green, and some red. We will see a colour there, and I'll show you which one it is. So there we have what happens when you add different colours of light together. And as you see, if you add, it's like a Venn diagram, if you add blue, green, and red, you get white. But if you add blue and red without green, you get this guy, magenta. And if you add blue and green but no red, you get cyan. And if you add, what are the others, the 2 ones remaining, red and green but not blue, you get yellow. And magenta is actually an example of what's called an extra spectral colour. It's not on the spectrum. I go back to it, you'll see it's not on there. Point to it, it's not there. It's actually due to the fact that only some of the colours are being added together that you see. And the absence of green with all the others gives you magenta.